Okay, Assalamualaikum and good morning. Sorry for the delay. I had some discussion just now. So let me share my screen. Can you see my screen now? Somebody? Okay, great. So I'll be using the whiteboard as you probably know, I'm still very behind in my typing up the lecture notes, but it's going on. So today I'm going to discuss about. Remember, we are still in this chapter of canonical ensemble. So the last thing that we did was to look at the previous lecture was canonical ensemble of spin half was two-level system, and that plus case. Okay. So today we're going to look at a different one, but in a way it's also simple in the context of how the energy levels are being solved. So let me write that down. So we are looking at single particle in one-dimensional box. So this you probably have learned in quantum mechanics. Okay, so we have a particle in 1D box. Okay. So we will mention what this means in a minute. So, but now we are doing a canonical ensemble of it. So then we will replicas of this particle of 1D box. Okay. Ensemble of m copies of such a system. So one should write also this assumption that we need in a way so that this will be later on discussed in a different chapter. Okay. So each particle is localized in each box. Its own box. And then each box is going to be distinguishable. So you can actually know which box a particle belongs to. Okay. Some assumptions. So what we're going to do is to recall, okay, how do we do it for the case of the two-level system before, is to write down the energy level. So we need to find energy levels. So let me move this thing up. So essentially this is by solving a Schrödinger equation. Just in case you forget, I'm going to write down. So generally we have this as your differential equation that you need to solve. Okay. X. And essentially the first term is the kinetic energy, second term is the potential energy. So basically this is the whole thing is going to be representing the total energy, and the eigenvalues that we need to solve is on the right hand side here. Okay, so this is the energy eigenvalue. So normally what one does is to solve simultaneously the energy eigenvalue with the energy eigenfunction. Okay. So this very much if you remember, this very much depends on what this we need to specify the potential. Okay. So in the case of the particle in a 1D box, it's quite easy to do. So particle in 1D box, which really models a perfect, what we call perfect confinement. I mean, it stays in that particular box without going out. Okay, and the potential that can do that is essentially the following. So Vx equals to, so the inside the box, okay, the potential is 0, so the particle is moving freely inside the box, okay, which is written as the interval between 0 to L, and outside the box, okay, outside the box we put it as infinite, so that essentially there is no chance of the particle going out of the box, because if you remember in quantum mechanics, if your potential is not high enough, then your particles can actually tunnel through. Okay, so we are avoiding that, so we need an infinite potential outside the box. Oops, I don't want to do this. Sorry about that. Okay, so what happens over here outside the box, can't have any particle, have the possibility of the particle there. So in other words, if you try to solve it by right, you should have imposed the wave function outside the box is going to be 0. Okay, so that implies at the boundary of this box, so there must be some boundary condition. And the boundary condition just impose continuity here, continuity of phi, okay, and that gives you this condition of phi of x equals to L has to be equals to 0, which is the wave function outside the box, and similarly at phi x equals 0. So in a way, this boundary condition allows the wave function to be continuous at the boundaries. Okay, so the only way that we can solve this, and remember, inside the box your potential is 0, so in other words there will be so in other words, inside the box, maybe I should just write this thing down. Inside the box, you're supposed to have sinusoidal function or plane waves. So plane waves subject to this boundary condition, so you can actually write down the solution to be the solution to be standing wave solutions. For details, you might want to refer back to your notes on quantum mechanics, standing wave solutions. And they are given by this, given by this what you call wave function, which is given by sine n pi x over L, where n is an integer and it's positive. Now you might say, why not negative, why not 0? If you have n equals 0, then the wave function is just simply 0. That means there is no particle inside. If it's what you call n is negative, then you remember that the sine function, for example, will be just the negative of the original function, okay? And this is just an equivalent way, because your wave functions are subject to a scalar multiplying the wave function, so that will define the same physical wave function, okay? So differs by a scalar. Scalar over here is -1, and physically it is the same state. Okay, so okay, if you know what the remember that these are essentially energy eigenfunctions, then one could actually write down the energy eigenvalues. And they are given by the following: epsilon n equals to, n is labeling by this integers thing, okay? So again, the details, you can look how to solve the Schrödinger equation in your quantum mechanics notes. I'm not going to do that. I'm just going to give it direct here. Okay, so it's going to be depending on this quantum number n, which is square of it, okay? So one can write the whole thing. The rest are all just constant. H bar is constant, pi constant, L is constant, m is constant. So you can write this as alpha n squared. And just to justify some approximation that we want to do later on, we'll do some estimates over here. So the estimate for electron in a box of length 1 centimeter, then your alpha is going to be, okay, so your H bar is this 1.054 times 10 minus 34, so yeah, minus 34 squared, and then your pi squared, and then 2 ml squared, 2 times mass of the electron, which we know as 9.11 times 10 minus 31 kilograms, and then length 1 centimeter is 10 minus 2 meters, so that is 10 minus 4. and this is roughly about 6.0 times 10 minus 34 joules. Now, one could also write this in terms of temperature. So you can write it over here just to make it depends on temperature here. So here you divide this alpha by the Boltzmann constant. Remember, okay, I should have mentioned that your alpha carry the dimension of energy. Okay, so the dimension of energy divided by the dimension of Boltzmann constant will give you the dimension of temperature. So that gives you around 4.4 times 10 minus 11 K Kelvin. Okay, so these are pretty small numbers, very small numbers. One could try to see, okay, how does this depend on the temperature, for example, or how does this depend on your size of the box. So one can calculate a few more quantities. So here, let's call this T here. So for, say, T at room temperature, okay, your alpha on KBT, okay, so I'm going to define this constant called gamma here, so that you get this dimensionless thing, and this is equals to 1.5 times 10 minus 13. Okay, so these are quite small again, and if we try to shrink the length of the box, okay, let's consider L equals to 10 minus 6, or 1 micron. Your gamma in this particular case, if you shrink the box at that temperature, then you should still be getting a small number, which is 10 minus 5, still small. So if one wants to have some comparable larger number, say your gamma is of the magnitude gamma comparable to 1, for example, then one requires smaller lengths, and or much lower temperatures. Okay, so what's the point of all this? The idea is now we need to, once you have the energy levels, you need to work out the partition functions. Okay, we call from energy levels one can get your partition function. Okay, so let's write that down, and just to highlight this particular property so that one understand what one is writing down is just a partition function that corresponds to a particle moving in a line. Okay, so it's a 1D case, and there is only translational motion. One should be careful that when you go beyond one dimension, there will be other types of motion that we need to take take into consideration. So here it's fine, it's just translational. Okay. So we're going to write it down as Z translational. Okay. Then this equals to the sum of E minus epsilon n, where this is the energy levels, divided by kBt. This is coming from your Boltzmann distribution thing. So and this is going to be sum between 1 to infinity. Or I can write this, we have already defined your gamma previously, then this is sum over from n to infinity of E minus gamma n squared. Remember that your epsilon contains some constants and then multiplied by n squared. Okay, so this is the kind of sum that we want to do, but no, the fact that gamma is always small, so that going from one level to another level is actually very close to each other. So recall the small nature of gamma, and then of course that implies exponential of minus gamma n squared even smaller. So what can one do is to replace this sum by an integral. So this is an approximation here. Oops. Trying to write too fast. Approximation sum replaced by integral. Because the going from one level to another is just a small number. So so what we're going to do is to write down your Z translational, which is initially that sum, to be roughly given by the integral from 0 to infinity exponential minus gamma n squared dn. And this is just an integral over the Gaussian function. So recall, so maybe a side here. Exponential, I think probably you have also seen this in quantum mechanics, exponential minus m squared, I think m squared, x squared dx from 0 to infinity is root pi over 2m. Okay, so we use this formula to get the answer for this, and this would actually give you root pi over 4 gamma. Okay, and just putting back all your definition of your gamma here, so that gives you L squared m kBt divided by 2 pi h bar squared. Okay, so next thing to do is, let's write this, and probably I've seen it somewhere. I'm not sure whether it's discussed in quantum mechanics or not, you can write this as, remember your Z translational is a quantity which is supposed to represent the normalization of your probabilities, so they are dimensionless. So I can write your Z translational here as the following dimensionless quantity. So first of all, it has to depend on this L. So I'm going to write as L, okay, divide by some wavelength written as lambda d here, where lambda d equals to square root 2 pi h bar squared over m kbt, and this is sometimes called the thermal de Broglie, actually it's pronounced differently from the way it's been spelled. Thermal de Broglie wavelength, which is really a thermal average wavelength. Thermal average wavelength of free particle of momentum P. Well, usually your thermal de Broglie wavelength are considered in terms of a 3D thing. Okay, so, but despite the fact that we are actually doing 1D here, the idea of thermal average is actually corresponding to this 3D. So okay. So what else after calculating your partition function is you should be able to calculate your free energy. Okay, so your free energy, we recall back, is minus kbt log z. So in this case will be log z translational. So you just plug in this expression, log of L squared m kbt divided by 2 pi h bar squared to the power of half. Right? Let's just go back. Oops, I don't want to do that. I want to bring this thing down just to check. Yeah, square root there. Right. Okay. So once you have free energy is already a thermodynamical quantity. So one could actually try to express other thermodynamical quantity from the free energy. One of the things that we should be interested in would be the entropy. So entropy is given by minus partial F partial T. So you differentiate your free energy with respect to T here. So there are two dependents on T here. One is from this factor and the other is from the T inside the log. So let's differentiate them. The first one should be easy. Excuse me. Log of L squared m kbt divided by 2 pi h bar squared to the half. And then the log something to the half, I can bring out the half in front, so I should be having I should be having plus here, so I should have also plus here. So I'm going to just this one is not going to be differentiated now, so that will be there, kbt, and then I differentiate this thing, and then I use the fact that I can pull out the half in front, so I have a half there, and then I just simply take the derivative of the log, and the derivative of the log will be the reciprocal of this, so I will have 2 pi h bar squared over L squared mkbt, and then remember over here this is something is a linear function of t, so we need to differentiate that as well, like a chain rule. So I'll get L squared mkb divided by 2 pi h bar squared. So this, you can see, cancels with that. This part will cancel with that. And you're left with, so there's a factor of half here. I can bring again the factor of half outside. So I'm going to pull out the common factor of half. And also another common factor is the Boltzmann constant, so half kb of log L squared mkbt over 2 pi h bar squared, and then this one will be just a half, so that gives you plus 1. So we have actually calculated the entropy of the case of the ensemble of particle in 1D box. And from entropy you can calculate other quantities. The other one that was calculated in the book was to actually calculate the heat capacity. So what the heat capacity in terms of the entropy is given by T times partial S partial T constant volume. And again, we already have the expression for the entropy here, so you just simply differentiate with respect to T. So remember we have that T outside, so that T is there. Then again, it's the same kind of thing. You have the log that you need to differentiate. So 2 pi h bar squared on L squared mkb, and then differentiating the linear function there, then I will have L squared mkb divided by 2 by h bar squared, and this will just give me half kb. Okay, the t, where is the t disappear? Oh yeah, I've forgotten the t, sorry. Okay, so that t is going to cancel with that t and leaving you just a half kb. So in other words, translational motion of a single particle gives contribution to specific heat, contribution to heat capacity, of only half kb. And this we will try to relate to the point of when you look at the average energy later on. Probably you can see that this is coming from the number of degrees of freedom multiplied by kVt divided by 2. Okay. So right. So what's next is to generalize what we have done to the case of a particle in a 3D box. So let's finish that for today at this. Again, if you have done quantum mechanics, you know how to do this. So generalize the 1D box potential to a 3D box potential, and you can actually solve it. But this amounts to just generalizing the wave function that we had earlier. Let me write this properly. 5. I'll explain why we have a subscript there later on. X. Now in 3D there will be the three variables of x, y, z, and then you just simply, your E is your normalization constant, and then you just simply multiply the standing wave solution in 1D 3 times. Okay, but now each variable will have its own integer, so in other words, there will be many different configuration that is possible coming out from your integers n1, n2, and n3. Okay, so in other words, we say the configuration I here, configuration I here correspond to the configurations of the triplet of these quantum numbers n1, n2, and n3. Okay, so you have to figure out, and then also if you remember, there is possibility of degeneracy in here, so you have to take into account of those. Now what else? So I think I'll just write down. Okay, writing down all the. Okay, let me just write it down. So in other words, so from there, phi I is simply identified with this eigenstate which carries these quantum numbers. Okay, so I think you probably have seen this kind of notation before. And if one looks at the eigenvalues over here, it's now given by h bar squared pi squared on 2ml squared, and the sum of this square of these numbers. Okay. Again, the details you should be able to see that from your quantum mechanics notes. So okay, in other words, we should be able to write down the partition function given that you have these energy levels. So so let's do that just for now. Okay, and remember, these are coming directly from just generalizing your translational motion. Okay, remember the 1D case, that's only translational, so you are not taking into account of other possible motion that can exist in 3D, so one should be very careful about that. So the partition function over here is for translational 3D motion, where for each what you call degree of freedom, there is possibility of that translation in that direction. So let me just write down what it is. So Z translational here equals to the sum of all possible n1, n2, and n3 of exponential minus gamma is coming from that constant there, times n1 squared plus n2 squared plus n3 squared. But then this addition of these exponents over here, you can simply write that down as the product. So in other words, I can separate it out as follows. Oops. So here is your translational partition function in the x direction, for example. Then second one is partition function for translational motion in your y motion, and finally for your z. So in other words, note here z translational factorizes. This is an important property that one finds regarding about the partition function. Now remember, we have actually given an expression of each of these terms or each of these factors. So oops, not that. So let's just recall. Sum e minus gamma n squared for n. So this is 1D case. We have actually replace it by an integral, and then you get this L squared mkbt divided by 2 pi h bar squared to the power of half. Okay, and then of course now we just simply plug in this expression into each of these terms because they are just multiplying each other. Then you have z translational for the 3D case will be well, bringing out the L cube out, and then I have m kbt divided by 2 pi h bar squared, and since it's been multiplied 3 times, I will have 3 over 2. Okay. And L cube essentially is the volume of the box. So I can write it in terms of the volume then. And remember, volume is actually something that you can actually measure. In this particular case, it's another one of those thermodynamical variable. Okay. So we found the partition function, and of course once you have the partition function, you can now calculate your free energy of particle, translational particle, meaning the only motion that it does is translations in volume V. Is given by F equals to minus kBT log Z, and one can write that down explicitly as log V coming from there plus 3/2 3/2 coming from that what you call exponent there, so and then you have the log okay. And this is a good start for you to calculate other thermodynamical variables. Particularly now we have this dependence on V. You know, for example, your pressure, recall your pressure is given by the partial derivative of your free energy with respect to V at constant temperature. And if you just simply plug in, there's only one factor or one term here that depends on V, and that gives you kBT over V. Or rearranging that, one has PV equals to kBT. And this is the pressure, your P here is the pressure from a single particle in a gas. So if there are n particles, then you just simply multiply them. For n particles, then you just simply get PV equals to n kBT, okay, and n is the number of particles over here. So if you have 1 mole of gas, then your n equals to your Avogadro's number over here. So you have PV equals to NA-kBT, and this can normally written down as your gas constant RT, where R is essentially just NA-kB. So for n moles, again you can generalize it again. N moles of gas, then you have PV equals to N RT, which is the thing that you have learned about ideal gas. Okay. So I think that's probably, let's see what else is there. Oh, yeah, we have just only calculated pressure. One can calculate other things like entropy. S equals to minus partial F partial T, constant volume. and this is given by going back to the earlier expression of the free energy. So this is log V plus 3 over 2 log mkbt 2 pi h bar squared plus 3 over 2. Okay. If I'm not mistaken, I might be wrong on this, so I think there's a name for it. Let me just check. This is called circle electrode equation. Let me just check about that, just in case I'm wrong. Oh, this is okay. Sacred that electrode 1 would have 5 over 2. I think that comes from another consideration which we have not done yet, which is I think probably is coming from the indistinguishability thing. Okay, so I better not say that. Okay, so that is the entropy. Finally, you can also from entropy you can actually calculate your heat capacity. Cv equals to T partial S partial T, and this is 3 kb over 2. So this can be compared with the case of the 1D case. We have only kb over 2. Over here you have 3 halves kb. Okay, so and this is the contribution of a single particle. Okay. For n particles, then you're going to get Cv equals to 3n kb over 2. Okay, so as I said, this later on we'll have to modify this to include indistinguishable later. I think it's the next chapter really that need to modify. Modification to include indistinguishability, meaning you can't distinguish between one particle with another. So I think this would be a good place to stop. Please try to get, we have missed about 2 hours of lectures, so let's try to replace at least 1.5 hours. If you can find a time to do this, please discuss. So let me at this stage take your attendance list. Is anyone affected by the flood, by the way, just in case? Anyone? Anyone living in Shah Alam or something like that? I guess not. Okay. So nobody here. Okay, it's fine. So so again, I'm supposed to give you a lot of things, but no, I keep delaying things. So many things to do. Tomorrow I have a PhD YOR, so that that explains a lot. Okay, so I'll stop for today. Thank you, everyone.
canonical